Hello, space enthusiasts! Welcome back to our channel where we dive into the mysteries of the universe. Today we're tackling a colossal topic: how are galaxies destroyed? This phenomenon stretches across eons and involves forces of almost unimaginable scale. Stick around as we explore the cosmic events that can end an entire galaxy's existence. At the core of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole. Ours is named Sagittarius A, a colossal entity weighing over 4.5 million times more than our Sun. Typically, these cosmic behemoths lie dormant, merely nibbling on stray gas and stars that drift too close. However, every so often, they consume a substantial feast. During these episodes, gas spirals into the black hole, compressing and heating to extreme temperatures, surpassing 1 billion degrees. At these fiery heights, the gas emits vast amounts of radiation, cascading through the galaxy. This flood of energy heats surrounding gas reserves, thwarting the birth of new stars. Though the galaxy often settles back into quieter rhythms, the most severe outbursts can violently expel significant quantities of gas, stripping the galaxy of its star-forming potential. This doesn't outright destroy the galaxy, but it cripples its ability to birth new stars, potentially halting creation indefinitely. Galaxy clusters are the bustling metropolises of the universe, often housing over 1,000 galaxies each. These cosmic conglomerates are more than just gatherings of galaxies. They also encompass vast pools of a hot, sparse gas known as the intracluster medium, ICM. Despite being so rarefied that it would be considered a vacuum in Earth-bound labs, the ICM presents a substantial barrier to galaxies as they plunge into the cluster. This interaction initially triggers a flurry of star formation as shock waves compress the galactic gas clouds. However, as time progresses, the relentless pressure of the ICM begins to strip gas from the galaxies, similar to how debris is sheared from a meteor hurtling through space. This stripping process gives rise to what astronomers whimsically call jellyfish galaxies, named for their gas trails that resemble the flowing tentacles of a jellyfish. While most galaxies withstand their voyage through the ICM, some of the smaller ones may be entirely dissipated by this harsh cosmic environment. Galaxy collisions are among the most dramatic events in the cosmos, unleashing staggering amounts of energy. Our very own Milky Way is on a cosmic collision course with the neighboring Andromeda galaxy, destined to meet in cataclysmic fashion about 5 billion years from now. This merger, unfolding over hundreds of millions of years, is not merely a slow dance, but a tumultuous upheaval. It creates vast tidal tails, majestic streams of stars and gas wrenched from the galaxies and cast out into space. As the galaxies intertwine, a chaotic ballet ensues, with stars flung into the abyss through violent interactions. The climax of this cosmic saga occurs when the supermassive black holes at the heart of each galaxy converge, unleashing a torrent of radiation that ravages the newly unified galaxy. This formidable burst of energy strips away vital gas reservoirs, silencing the engines of star creation and marking an end to the galaxy's ability to birth new stars. When a smaller galaxy merges with a significantly larger one, the smaller galaxy often faces its demise. The European Space Agency's Gaia survey has uncovered what could be considered the cosmic graveyard of these devoured galaxies scattered throughout the Milky Way. A striking example is the Gaia sausage. This oddly named group of stars swirling around the core of the Milky Way exhibits unique characteristics, such as a rich composition of heavy elements and distinct orbital behaviors, setting them apart from their celestial neighbors. These stars are believed to be the fragmented remains of a small dwarf galaxy, mercilessly ripped apart and absorbed in its collision with the much larger Milky Way. This tale of cosmic cannibalism is not unique. Astronomers have cataloged dozens of other such remnants, collections, streams, clumps, all bearing witness to the turbulent and violent merger history that shapes galaxies like ours. These findings paint a picture of a universe where galaxies grow and evolve through these dramatic and destructive encounters. Over the vast stretches of cosmic time, galaxies, though remarkably resilient structures that have endured for more than 10 billion years, are not eternal. As the eons pass, the universe will age exponentially beyond its current state, and our future merged form of the Milky Way Andromeda galaxy will start to unravel. This process isn't sudden, but a slow consequence of gravitational dynamics at play. Stars, typically isolated from each other across vast distances, occasionally drift too close and engage in a delicate gravitational ballet. This dance can fling them into new trajectories, and very occasionally provide enough momentum for a star to break free from the galaxy's gravitational grip entirely. Such events are extraordinarily rare, yet given enough time spanning trillions of years, these rare occurrences accumulate. Ultimately, every star in our galaxy will either be swallowed by a massive black hole or be flung out into the vastness of the universe. This gradual dispersion or ultimate absorption will mark the definitive end of our galaxy as we know it. Galaxies are not static. They move and interact in a dynamic ballet governed by gravity. One of the most dramatic fates a galaxy can face is a collision with another galaxy. When galaxies collide, their structures can merge to form a single, larger galaxy, often resulting in a burst of new star formation. However, the individual identity of the original galaxies is destroyed in the process. This process, known as galactic cannibalism, can dramatically alter the shape and size of a galaxy. At the heart of most, if not all, large galaxies lies a supermassive black hole. These black holes can have masses millions or even billions of times that of the Sun. When material gets too close, it is devoured by the black hole, releasing vast amounts of energy. In some extreme cases, the black hole can disrupt the galaxy's stellar orbits or eject significant amounts of matter into space, which can strip the galaxy of its resources needed to form new stars, leading to its eventual demise. As galaxies move through space, they encounter the intergalactic medium, IgM, the sparse but vast gas that fills the space between galaxies. This interaction can strip a galaxy of its interstellar medium, the gas and dust that are crucial for star formation. Without these materials, a galaxy cannot produce new stars, and over time, as existing stars die out, the galaxy will gradually fade away. Galaxies can also die by a process known as starvation or strangulation, which occurs when they use up all their interstellar material for star formation and are unable to acquire more. This can happen due to isolation from other galaxies, or being located in a region of space where the intergalactic medium is too thin to replenish the galaxy's gas. Without new star formation, the galaxy will slowly burn out as old stars reach the end of their lives. Dark matter, which makes up about 27% of the universe, plays a critical role in the structure and formation of galaxies. However, its enigmatic nature means that it can also contribute to the destruction of galaxies. Theoretical models suggest that fluctuations in dark matter distribution can lead to gravitational instabilities that might disrupt the formation and maintenance of galaxies over cosmic timescales. Young, massive stars emit intense radiation and stellar winds. These forces can blow away the surrounding gas and dust, which are essential for star formation. Over time, this radiative feedback can deplete the galaxy's star-forming materials, eventually leading to its decline. This process is especially potent in smaller or less dense galaxies. Galaxies in denser regions of the universe, like galaxy clusters, experience more interactions and disruptions due to gravitational forces from nearby galaxies. These interactions can lead to tidal stripping, where a galaxy loses its stars and gas to a neighboring galaxy. This not only distorts the galaxy's shape, but can also eventually lead to its dissolution. As the universe expands, galaxies move away from each other. This recession can isolate galaxies, limiting their ability to interact and merge with others. Isolated galaxies may suffer from lack of material exchange and are more susceptible to internal processes leading to their decay. Supernovae, the explosive deaths of stars, can eject significant amounts of material into space. In a densely populated galaxy, This can lead to rapid depletion of the gas needed for new star formation, effectively speeding up the process of galactic decline. In crowded galaxy environments, smaller galaxies often undergo repeated, high-speed encounters with larger galaxies. Each encounter can strip the smaller galaxy of some of its stars and gas. Over time, these cumulative effects, known as galactic harassment, can dismantle a galaxy entirely. While dark energy's role is more about the expansion of the universe, its influence on galaxy structures over the long term cannot be ignored. The accelerated expansion of the universe can affect the gravitational binding of galaxies, potentially leading to changes in their structure and distribution. Galactic-scale magnetic fields can influence the dynamics of interstellar gas and the formation of stars. In some cases, strong magnetic fields can inhibit star formation by counteracting gravity, which can prevent the collapse of gas clouds into new stars, eventually leading to a galaxy's stagnation. As galaxies age, their stellar populations evolve. Older stars tend to be less massive and luminous, leading to a decrease in the overall brightness and visibility of the galaxy. This aging process can make a galaxy appear dead as it loses its vibrant, youthful characteristics. Quasars are extremely luminous active galactic nuclei powered by supermassive black holes. Their intense energy outputs can heat up a galaxy's gas, preventing it from cooling and collapsing into new stars. This quenching of star formation can contribute significantly to a galaxy's decline. Recent theories suggest that gravitational waves, ripples in spacetime caused by massive cosmic events, could influence the distribution and formation of galaxies. While the direct impact on individual galaxies is still a topic of research, these waves might contribute to structural changes over cosmic timescales. The chemical makeup of a galaxy evolves as stars process elements and release them into space. A galaxy may reach a point where the chemical environment is unfavorable for forming stars that resemble our Sun, affecting the types of planets that can form and potentially leading to less stable galactic structures. Active galactic nuclei, AGN, represent extremely energetic and dynamic centers of some galaxies. The vast energy they emit can lead to winds strong enough to blow away large amounts of a galaxy's star-forming material, affecting its ability to sustain itself. Galaxies can lose angular momentum through interactions with other galaxies, or the IgM. This loss can lead to a more rapid inward flow of gas towards the galactic center, potentially feeding the central supermassive black hole and disrupting the galaxy's regular star formation process. Similar to the concept of global warming on Earth, galaxies can experience a form of warming when their interstellar medium heats up due to various cosmic events and processes. This heating can prevent the gas from cooling and condensing into new stars, leading to a gradual fading of the galaxy. Satellite galaxies, which orbit larger galaxies, can experience orbital decay due to dynamic friction with the dark matter halo of the host galaxy. Over time, this can cause the satellite to spiral inward and eventually merge with the main galaxy. This process can disrupt the structure and star formation of both galaxies involved. Cosmic rays, high-energy particles traveling through space at nearly the speed of light, can have a profound impact on a galaxy's ability to form new stars. These particles can ionize gas within the galaxy, heating it and increasing its pressure, which prevents it from collapsing into new stars, thus contributing to the galaxy's aging process. This process involves the gradual transformation of a galaxy due to internal processes, such as the redistribution of mass and angular momentum within the galaxy. Over billions of years, this can lead to significant changes in a galaxy's structure, such as the formation of a bar or the transformation of a spiral galaxy into a more elliptical structure. In close galactic encounters, gravitational forces can cause tidal heating, where the internal energy of a galaxy is increased due to the deformation of its shape. This additional energy can heat the galaxy's gas, preventing it from cooling and condensing into star-forming clouds. The remnants of cosmic inflation, an exponential expansion of the universe shortly after the Big Bang, might still influence large-scale structures. If inflationary effects vary slightly across different regions, this could lead to variations in galactic formation and potentially destabilize existing galaxies. Stars do not always remain in the same part of a galaxy where they formed. They can migrate across different regions due to interactions with spiral arms or other stars. This migration can change the dynamics within the galaxy, affecting its stability and star formation patterns. Ultraviolet radiation from large active galaxies nearby can strip smaller galaxies of their molecular hydrogen, which is crucial for star formation. This process, known as photodissociation, can effectively sterilize a galaxy, preventing new stars from forming and leading to its gradual decline. While dark matter is the best-known form of exotic matter, other types, like dark energy or hypothetical particles like axions, could play roles in galactic dynamics. Their interactions could lead to unexpected gravitational effects or influence the dark matter halo of galaxies, altering their evolution. Over timescales of billions of years, the internal dynamics of stars within a galaxy can lead to increased instances of stellar collisions and mergers. This can significantly alter the mass distribution within the galaxy, leading to new and often less stable configurations. Gamma-ray bursts, GRBs, the most energetic events in the universe since the Big Bang, can have devastating effects on a galaxy. If a GRB occurs within a galaxy, the intense radiation can ionize its gas and significantly impair its ability to form new stars, leading to rapid aging. While still purely speculative, some theories suggest that interactions with other dimensions or parallel universes could have tangible impacts on our universe's galactic structures. These influences could manifest as unexplained forces acting on galaxies, altering their courses, or even leading to their disintegration. Background radiation left over from the Big Bang, primarily the cosmic microwave background, CMB, permeates the universe. As galaxies move through this radiation, interactions could potentially affect their internal thermal dynamics, subtly influencing evolutionary paths. Galaxies are not randomly distributed, but are part of larger structures such as filaments, walls, and voids. These structures can influence the movement and evolution of galaxies, with those in denser areas experiencing more interactions and potential disruptions compared to those in voids. Neutron stars in galaxies can produce intense magnetic fields and emit powerful jets. If one of these stars becomes active near a galaxy's dense molecular clouds, the resultant jets could disrupt star formation by dispersing the clouds, affecting the galaxy's long-term stability. Quantum mechanics suggests that on microscopic scales, vacuum fluctuations are common. If similar fluctuations could occur on cosmic scales, they might sporadically influence the stability of galactic structures, though such effects remain purely theoretical at this point. As stars end their lives and expel their outer layers, these materials form planetary nebulae. These events contribute to the recycling of material within the galaxy, but can also add to the dispersal of potential star-forming gas, affecting the galaxy's ability to regenerate. Solar winds emitted by stars, particularly massive ones, can drive material out of a galaxy's gravitational influence. Over time, this can reduce a galaxy's mass and disrupt its ability to maintain sufficient gas for star formation. In the far future, advanced civilizations might have the technology to deliberately alter their galaxy's structure for energy or survival needs. Such modifications could potentially stabilize a galaxy, or conversely, hasten its end depending on the methods used. If the universe has any form of cosmic viscosity, similar to air or water resistance but on a galactic scale, it could affect how galaxies move and interact. This hypothetical property would subtly sap the energy of moving galaxies, potentially altering their dynamics and lifespan. The interstellar medium within galaxies can become turbulent due to various factors such as supernova explosions, stellar winds, and interactions with other galaxies. This turbulence can disrupt the formation of new stars by preventing gas clouds from condensing, leading to a slow decline in star formation rates. Galaxies within galaxy clusters are subjected to intense gravitational forces from the cluster as a whole. These forces can strip away a galaxy's outer stars and gas through a process called tidal stripping. The stripped material often ends up as intracluster light, while the original galaxy may become a shadow of its former self. Massive stars, particularly in their later stages, can eject large amounts of material in stellar outflows. These outflows can carry away significant portions of a galaxy's gas, reducing its capacity to form new stars. Over time, this depletion of gas can lead to a decrease in the galaxy's overall brightness and star-forming activity. Supermassive black holes at the centers of galaxies can influence their host galaxies through feedback mechanisms. When these black holes actively accrete matter, they can emit powerful jets and winds that expel gas from the galaxy. This feedback can suppress star formation and alter the galaxy's evolution significantly. Galaxies are surrounded by dark matter halos, which play a crucial role in their formation and evolution. Halo quenching occurs when the dark matter halo heats the gas within the galaxy, preventing it from cooling and forming new stars. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.